Hey everyone, so I'm starting a hands-on series on using PyTorch, and in this video I will cover the basics. And trust me, if you are interested in deep learning, this series will be very useful for you. PyTorch is like Python for machine learning, flexible, intuitive, and incredibly powerful. It was created by Facebook's AI research team. It's one of the hottest tools in AI research and development. What makes PyTorch special? Imagine building with Lego blocks. That's PyTorch. You can build and modify your neural network on the fly. You can debug your code like regular Python code, go from idea to prototype super fast. A quick comparison with TensorFlow. PyTorch feels more like Python. It's great if you love Python and if you are working on an academic research or AI research project. TensorFlow is very structured and think enterprise ready. So if you are working at the enterprise level and if you're working on tools for deployment, fast deployment, then TensorFlow is great. Both are awesome, but PyTorch is our choice for learning because it's more intuitive. The best part, if you know Python, you're already halfway there. PyTorch was designed to feel natural to Python developers. So, ready to build something cool? Let's dive in and write some code. Hello everyone. So today in this tutorial, we will learn the fundamentals of PyTorch. We will cover basic tensor operations, the building blocks of deep learning, understand different types of tensors, and essential mathematical operations. And I will introduce the activation function in PyTorch. Let's import some necessary libraries. Here's what we are importing. We are importing NumPy for numerical operations, Matplot for visualizations. Torch is the main PyTorch library. The building block of PyTorch is the tensor. Tensor is just like vectors and matrices, is a fundamental concept in physics. So if you're coming from a physics background, you already understand intuitively what tensor is. But any dimensional matrix is known as tensor. We define scalar, like scalar is a rank 0 tensor. And we can, if we print it, you see it will give you the tensor 3.1. For a vector is a rank 1 tensor, just like force or velocity. The way you define the vector is again the same terminology, torch dot tensor, but inside it's not a single value, but it's an array. And then if you say print vector, the vector is equal to 1, 2, 3. Okay. Let's try some operations on the vector. The first operation we can do is the vector multiplication or the matrix multiplication. We can say vector multiplication. So the way we define the vector multiplication is using the at symbol. So this will give you 14. 14 is because it's a dot product in terms of vector. We can also take the power of a vector. And we can just say the way we take the power is by writing vector dot power. And let's say if I take the power by 2, this will give me the power of the vector. The power of the vector means like every element have power 2. Okay. The way we define any matrices, and matrix 2 by 2 matrix is a rank 2 tensor, 3 by 3 matrix is a rank 3 tensor, and by n matrix is a rank n tensor, is a similar expression, but now see the difference inside the torch.tensor, we are giving a 2 by 2 matrix. Okay. And if I say print matrix, it gives you the matrix. Okay, the same operations we can do with the matrix. Let's say matrix at matrix. So matrix multiplication by multiplication, it gives me a 2 by 2 matrix. Okay, or we can say matrix dot power, raise each element in the matrix by 2, and you see it gives me the same rank matrix, but each element to the power of 2. Let's suppose if you're working in physics problem, let's say a quantum mechanical problem, you can use tensors to do your computation. Psi in quantum mechanics is just a vector. It's called a state vector. We define a state vector, and then we define a tensor called h. H will transform the state vector. Then the matrix multiplication, which is the transformed version of the psi, it can be written as h at psi, and this will give you, so if I define this, and this will give you a quantum state transformation matrix. So this is the idea of using tensor operations. Here I will show, with the same physics problem, I'll show how we can calculate the gradients of any function. Let's define a potential energy. So potential energy is equal to half kx squared. Here I defined k is equal to 1. So let's define a function which takes x and will give you the potential energy. Then we define a torch tensor, and we say, okay, the gradient is equal to true. And then we define the potential energy given x. When we say, and x has a 0.2, let's say I'm just taking 1 point, but I can also take a lot of points in x. When we say v dot backwards, it will calculate dv by dx. Okay. So if I print this gradient at x is equal to 2, x dot grad, and it should be 2.0. Okay. So after v dot backward, I can just call x dot grad, and it will give me the gradient of v dv by dx. So now we come to the basics of neural network. The first thing we need to understand is the activation function. So for the activation function, we define x is so x is just an array from -5 to 5. We generate 100 random points. Then we define the ReLU. So ReLU is defined as torch.nn.functional.ReLU. So this will just call the ReLU functions. And then we can also define the sigmoid function. So sigmoid is equal to torch.sigmoid x. So for the plot, we can say xplt.plot x.numpy. X was a tensor, so we have to convert them into a numpy array. X.numpy will convert x into an x array. Then ReLU.numpy will convert the output of ReLU to an NP array, and similarly for the sigmoid function. And when we run this command, you will see it. You will see the two functions. So I think I have to remove this one. Two function. The orange one is sigmoid, and blue one is ReLU. So ReLU keeps the positive values, sets negative values to 0, and sigmoid squishes values between 0 and 1, and is useful for calculating probabilities. In the next tutorial, we will see how to build a simple neural network.